Good afternoon, my YouTube viewers. It's Crystal here. I just wanted to make another code review for you. I'm doing a code review on Jason Brownlee's shampoo data set. And what I'm doing is I'm doing the code review on the Stats Model's Arima method. And I'm checking it without differencing and then with differencing to see which model gives me the best outcome. And so that's what I'm going to do, because the Arima model is a combination of auto regression and moving average with differencing, or integration is the I. And then so basically what happens is your AR gives you your P parameter, your MA gives you your Q parameter, and your inference or your differencing gives you your D parameter. And so you have to set up parameters on the Arima data set to get it to work. Sorry, the Arima model to get it to work. And that's what this code review is going to be all about. So we did the I did the program on Google Colab, which is a free online Jupyter notebook. And so there's not really any excuse for somebody with the internet not to be able to program in Python, because Google Colab is free. They don't have to pay anything for it. And then so after I created the program in Google Colab, I would like to say that it doesn't have a very good undo function, so you have to be very careful not to delete or overwrite any valuable code, because you may lose it. But you do have in the edit function, you've got to undo cell, so you can undo a cell if you delete the cell. And if you come over here to your save history, you can go into the save history and look through the save history, and there's a possibility that you might be able to retrieve the deleted or overwritten code if you look in the save history. So that's one thing that you can do if you accidentally delete or overwrite code. And I have done that before. I have overwritten code accidentally. So it's something that can easily be done if you're not careful and you're not concentrating on what you're doing. So after I have created the program, the first thing you want to do is you want to import your libraries. So we're going to import Pandas, which is a data processing library, and it creates data frames and maintains them. We're going to import NumPy, which is a numerical library, and it does numerical computations as well as creating NumPy arrays. We're going to import Math, which is an inbuilt library in Python that performs mathematical computations such as square root. We're going to import Stats Models, which is a statistical model with Python. We're going to import Matplotlib, which is a graphics package, and it plots the data points onto a graph. And we're going to import Seaborn, which is a higher level graphics package, and it will compute statistics as well as plotting the data points onto a graph. So that's a nice thing about Seaborn. And we're going to import the warnings so it won't give us warnings all the time when we're working on the program. And then after we've imported our libraries, what we're going to do is we're going to load up the file. And what I did was I used Jason Brownlee's file from his GitHub account. So that's Jason's Brownlee file. So header equals 0, parse dates equals 0, squeeze equals false, date parser equals parser, and index call equals 0. So this is your series. I turned it into a data frame. So your index is your month, and your sales is your actual time series. We're going to check on the info of the data set, and you can see it's got one column, which is a float, and the index is a date time index. We're going to check for null values. We don't have any null values. And then we're going to chart the time series onto a graph, so you can see that this chart, it definitely has a trend. It has trend and it has seasonality, but definitely trend. And it looks to me like it's an additive trend. We do a disk plot of the time series, and so you can see that the disk plot of the time series. I just wanted to look at it at two values so you can see that the shampoo sales are increasing every month. You can see that, but I just wanted to look at it on both sides of the zero, because since all of the values are going to be either zero or positive, they're not going to have any negative values. You can actually view your data set on both sides of the x-axis. Then what we wanted to do is we wanted to check to see what the shampoo sales were each month. It looks to me like you had the most shampoo sales in September and December. And you had the least shampoo sales in February. February you had the least shampoo sales. We want to check the shampoo sales on the day of the week. It looks to me like you had the most shampoo sales on a Tuesday and the least shampoo sales on a Saturday. You wanted to see what the shampoo sales were on the week of the year, and that's a bit difficult, but it looks like week number 36 that had the most shampoo sales. Now what I'm going to do is I'm going to delete all the unnecessary columns to take the time series back to just having an index and a sales column. So now we're going to do just some tiny statistics, not major statistics, but tiny statistics, which, so your maximum value is going to be 36, 32, and then your minimum value is going to be 3. And, the maximum value on the month is going to be month number 32, and the sales is going to be 682, and the minimum value is going to be month 3, and it's going to be 119. Now we're going to smooth it over a 12-month period, and so you can see how the time series is smoothed using smoothing. Now we're going to split the data frame up into a training and test set, so you can see that the training set has 32 rows by one column and the test set has 4 rows by one column. Now we're going to employ the Arima model without differencing, and so you've got your PDQ, your P and Q go up to 7 and your D goes up to 2, and I've got the code here. What I did was I put the code in remarks, but you can copy the code and use the code yourself for your own Arima models and just take the remarks out, and that will work, just so long as you've got like the training test and set, as long as you've got the training test sets correctly coded in the for loops, it should work fine. But I remarked it all out because it does take quite a while to do it, and I did it this morning. So now we check stats model on the Arimas, and so we put it in the model. We trained and fitted it with an order of 102. So 102 means that it didn't do any differencing. And now what we did was we made predictions on it. So when we made predictions on it, what I did was I plotted it onto a graph, and you can see that the predictions were pretty much where the actual values were. And I think what I'm going to do here, since I don't have a next training and a next test, I'm just going to take that out. So next time I do it, it'll be train and test and not X train and X test. And so now what we wanted to do was I took the test in the white hat and I converted it to a data frames because it needed to be in a data frame for whenever I checked my error. And I did put in a code to check the error and had a 96 points RMSC, which was very good. And then I put the actual test and well, that's not right either, white hat. So it looks like I'm going to have to do it all over again anyway. Let's try it. Hopefully it won't crash on me. Let's see what happens. So it did crash on me, but let's do this. I remarked it out, and that's what caused it to crash. So I'm going to unremark these. And we'll try it again. That's a good thing about doing these code reviews, because if I do a code review, I find mistakes that I've made. So we still had a RMSC of 96, which was good, but this hasn't worked out very well. So let's try this. Data must be one-dimensional. Try it again. It says data must be one-dimensional. See what it says here. So white hat is 2 dimensions. And test is 2 dimensions, but it says that it doesn't have, flatten. Let's try it. Let's try restart and run off. And let's hope for the best. Series object does not have flatten. I think Ravel is another thing you can use. Let's try Ravel. No. Let's see what we've got here. try it. It says it's a series. It says, what does it say? It says, data must be one-dimensional. Let's try this. Let's try. Hmm. Let's try this. Now it's saying data must be one-dimensional. You just can't win, can you? So it says it doesn't have values. So it's still two-dimensional. Well, let's try it again. It says data frame object has no, it says it doesn't have a flatten. You just can't win, can you? I wonder if flatten is deprecated. I just wonder if it's deprecated. But you've got, y hat is 2 dimensions and test is 2 dimensions. It says Ravel, and it wouldn't do it. It didn't do Ravel. It didn't do flatten either. It didn't do flatten and it didn't do Ravel. Yeah, it said it doesn't do Ravel. Data frame object has no. Let's try this. For Y in test. Okay. For Y in test cells. So let's try this. It worked. So we finally got it to work. Try that. So it wouldn't round it. It won't round it. But it did do this. So we did get it to work eventually. And that's one of the problems with programming is you have to just keep trying and trying until you finally get it to work. So we spent all this time trying to get it to work, but we finally got it to work. So now what we're going to do is we're going to check for stationarity, and it isn't stationary. And since it isn't stationary, what we did was we used differencing to make it stationary. And then, so we created a new column called stationary, and you can see what the difference time series looks like, and the difference time series looks a lot different from the original time series, so we'll give you the original time series. This is your original time series. And and this is your difference time series. So now this is just going to be to reverse the differencing, so you can see how you reverse the differencing, because you will have to reverse the differencing at some point. And that's another problem that you're going to have, because if you difference a time series, you're going to have to go back and reverse the differencing as well. So this is the sales column, and this is the reverse difference column, and you can see that they're the same. And you can see here in the data frame that I created, the sales column is the same as the reverse difference column, except that it doesn't have, it rounds it. We're going to say float. We're going to make that a float. And so that'll make it, it'll make it, yeah. So you can see it's a float now. And you can see that the values are the same. Okay, so now what we have to do is we have to split the data frame again, because we've done so much work, the data frame has gotten confused. So now we split it again, and we use the exact code that we used at the beginning of the program. And now what we're going to do is we're going to do some more statistics. We're going to check the mean and the variance of the test and trains. So we check the mean, and there's a difference between the mean is negative 318 between the test and the train. So you know there's a difference there. And then we're going to check the variance, and the difference between the variance is 4713. So you can see that there's a difference between the mean and the variance now. So that means that the data set is not stationary. We analyze the test set. So this is what the test set looks like after it's been differenced. And we decompose the seasons. We use seasonal decompose, so you can see that the observed time series, you can see there's an upward trend. You can see that there's seasons in it, and you can see also there's residuals, which is kind of like noise. Now we're going to do the Arima method again, and so we're going to use that grid search again. And when we did the grid search, we got about order of 210, which was different from the grid search order that we had when we didn't do any differencing. So when you do differencing, your grid search is going to be different. We're going to make our predictions, and you can see here that and in addition to that, we had to reverse the differencing. So remember earlier on in the program we reversed the differencing. So you can see here that we had to reverse the differencing. But I'm not going to make this an int. I'm going to make it a float. And then, so you can see that when you do your own differencing, and then you do the Arima with your own differencing, you can see a difference between the predictions with when Arima does the differencing and when you do the differencing. And another point that I would like to make is it said here, it said 210, but when we did the original Arima, the middle one, which was the P, was a 0. So the middle one, Arima didn't even do any differencing but in the beginning, but now it's having to do differencing. So that means that this data set has been differenced twice. It was differenced once when we did it, and then it was differenced again in Arima. But in the previous Arima, it didn't do any differencing at all. So that's another problem. When we did the Dickey-Fuller test, the Dickey-Fuller test said that it wasn't stationary. But is that true? Is that correct that it's not stationary? Because if it wasn't stationary, then Arima wouldn't need to do any differencing. So we did the differencing once, and Arima did the differencing once. So that's a problem. and then we check our RMSC, and it's 290. So our RMSC, when we do our own differencing, is like 3 times more than the RMSC when we don't difference. So that means we have a lot more noise. I'm just going to run this one more time and hope for the best because I set it up for float. Yeah, so I set it up for float. So you can see here we had an error RMSC of 290. But when we go to without differencing, we had an RMSC of 96. So the error without differencing was a lot better than we had the error with differencing. So what's that? And you can see right here, the D, there was 0 in the D. So you can see right here, is that Dickey-Fuller test correct? Because that's what the Dickey-Fuller says. If the p-value is greater than 0.05, it's said to be not stationary, and you have to do differencing to make it stationary. So that's another problem that we have. But so what it's saying is you don't need to do differencing when you use the Arima model, and you get a better noise figure when you don't do differencing with the Arima model. So that's it. That's it for this video. Thank you so much for watching me try to solve this problem. So we did troubleshoot the problem, and hopefully you got some more programming ideas watching me try to troubleshoot the problem. And thank you so much for watching this video. I would like to thank all of my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. And I look forward to making more videos for you in the future.